Hello and welcome to this EE228 video where we are going to solve differential equations and introduce the concept of zero state and zero input responses. To start off, I want to re-examine this generic linear constant coefficient ordinary differential equation from last video. This is n derivatives of y on the left is equal to some combination of derivatives of the input forcing function x on the right. So the big takeaway from your classes in differential equations, or one of them, would have been that the solution of a differential equation is any function y that when you plug it in for this y left-hand side, you get equality with whatever is here on the right. In addition, you get the initial conditions are also met. So any function you find that does both of those things, that is the solution. Right? That was the special case why linear constant coefficient ordinary differential equations are nice, is because they have unique solutions. So how do we find those solutions? Well, they usually come in two parts, and this was another big takeaway, that the total solution, or sometimes called the complete solution, is often written as the sum of a homogeneous solution with what we call a particular solution. So I'm going to call this YH, and I'm going to call the particular Y sub P. So how do we find the homogeneous solution? Well, that's, by virtue of its name, it is the solution if the problem were a homogeneous diffie Q. That is, if the right-hand side here was a big fat 0. So if that were going to be the case, then we would be looking for a Y that when we take linear combinations of it with its derivatives, we get 0. And if you think about that for a little bit, you recognize that the only function that obeys that kind of principle is an exponential. So let's try the most generic exponential we can think of. It has an arbitrary time constant up here, lambda, and it's got an arbitrary scaling factor, c. So if we try this function in the homogeneous part of our given diffie Q, then what happens when we differentiate this function n times? Well, that means the lambda will drop down n times, so we'll get c lambda to the n e to the lambda t. Now I want to add that to a sub n minus 1 times the homogeneous attempt after n minus 1 derivatives. So that would be c lambda to the n minus 1 e to the lambda t. Now keep doing this until you get down here to the first derivative. That would be a1 c lambda e to the lambda t, and then the original function itself scaled by a naught. And if we're solving the homogeneous diffie Q, the right hand side is 0. Okay, so a lot of things are in common between all these terms, right? C appears everywhere, so we can factor it out. And if it's 0, then that's not particularly exciting. But that does mean that the 0 function is the solution of any homogeneous diffie Q. But that's just because 0 plus the derivative of 0 will just equal 0. So that's not really an interesting solution. So the other thing that is common is the e to the lambda t. So you can factor that out. And for no finite t, will those all be 0? So what's left is what we call the characteristic polynomial. So we got lambda to the n remaining here. We got the coefficient a n minus 1 times lambda to the n minus 1 plus all the terms in the middle plus a1 lambda plus a naught. So as I mentioned, this by itself is peculiar to the system, right? That is, if you change the system, it will change. So it's called the system characteristic polynomial. And if we bring down this equals 0, then it becomes the characteristic equation. And this is powerful because it's turned the study of a differential equation, which will have an answer that is a function, into the study of a single polynomial, which, if you look at it as it equals 0, we're just trying to find the n possible lambdas that make this true. So we call those lambdas, so the roots of the characteristic equation are called the characteristic roots, and we're going to number them 1 up to n. I'm going to call them little r's. So they are the values of lambda that make the characteristic polynomial equal 0. And I know there will be n of them because of the fundamental theorem of algebra. So, but that also means that each individual root makes this left-hand side 0. So they are all potentially homogeneous solutions, which is why we allow ourselves to take all of them in some kind of linear combination. So we started with a guess of one homogeneous solution, and what we ended up with are n possible homogeneous solutions. Because each of these will work, that means that a certain scaling factor will also work, and it also means that if we take sums of them, it will also work. And by work, I mean they will satisfy this left-hand side differential equation equals 0. So this is what I want to call the system's homogeneous solution. Now, on the other side of the equation is the particular solution. So the particular solution usually is thought of as the response due to the forcing function. And the motivation for thinking of it this way is that the homogeneous is typically going to be a transient type response, right? These e to the rt's are either going to, well, they're going to blow up if r is positive real part, or they're going to decay away if r has negative real part. They could potentially oscillate forever if r has 0 real part, but for our purposes, it suits us to think about the particular solution being how the system will look in steady state, right? After whatever is going to die off has died off, the forcing function will remain. And so that's the motivation for saying the particular function, sorry, the particular response in some sense always looks like the forcing function. And these are the solutions where you would look up in the tables, like if the forcing function is a constant, then the particular will be a constant. If the forcing function is a sinusoid, then the particular will be a sinusoid. If the forcing function is an exponential, the particular will be something like an exponential. So I think it's suitable now to try and tackle a small example. So let me scroll down and we can try that. The example I want to tackle is given by the following differential equation. It's first order. It's dy dt minus y of t equals x of t. And first off, I want to consider the forcing function to be the unit step. And I would like to solve this for the initial condition y of 0 is 1/3. All right. So first things first, let's find the homogeneous solution. So that'll be 1 times lambda. So I have a 1 coefficient here, and I have a first derivative, so that's lambda to the 1, minus 1 lambda to the 0, because 0 derivatives equals 0. So this is, of course, lambda minus 1 equals 0, so my one and only one root is positive 1. So our best guess at the homogeneous solution is some constant times e to the t. Now, one thing that I may have glossed over is that I'm only interested in solving this for times greater than 0, right? I'm given an initial condition at time equals 0, and I'm given a forcing function that really only exists and is non-zero for positive time. So really the task here is to find the total solution for positive time. Because the assumption is if you're not forcing it with anything and you're not exciting it with anything, then you don't lose anything by assuming the total solution is 0 at negative time. So you will occasionally see me write just tack on step functions to all of these, because I only intend them to be accurate for non-negative time. So this was our homogeneous. If we now look at the particular, we have to ask ourselves what kind of function looks like a step function. And here is where we have to get a little bit more technical about what I mean by looks like. The only thing that looks like in our book a step function is a scaled step function. Okay, so if you let time go to infinity, the only thing that will, if you squint your eyes, look like a step will be a step or some scalar value of that. Anything that changes with time won't look like this. So in order to find the forced part of the solution, and what I'm going to do now is I'm going to talk about the total solution being attributed to two parts. We talked about the homogeneous in the particular, but then we can also talk about the forced response and the natural response. So the forced response is just the response due to the forcing function. So it has to take yp, the particular, and it has to satisfy the original non-homogeneous differential equation. All right, so here I've got my homogeneous part, I've got my forcing function. If I look to differentiate yp, I'm looking for the derivative of a constant, which is 0, and then here this is du of t equals u of t. So from here I can conclude that d has to be -1, and that means that my forced solution, or the part of the response that will satisfy the forcing function, is negative u of t. Okay, and that kind of makes sense. If we look back here at our original problem, what kind of function, when you differentiate it and then subtract itself from that derivative, equals a step? Well, it would be something that was 0 minus a negative step gets you a positive step. Okay, so that kind of makes sense. And next up, we're going to address the natural part of the solution, because what we haven't done is we haven't satisfied these, or this initial condition, right? If we were just stop here, yf at 0 is -1, which doesn't meet our initial conditions. So what I like to do is I like to think of natural as somehow the extra needed to satisfy the initial conditions. Right? The forcing function takes care of the forced solution takes care of the forcing function part. The natural would be whatever you need to make up the difference and satisfy those initial conditions. So here it helps to start with writing out that the total solution will be the forced solution that we just found plus some form of the homogeneous. And it's the total solution, when evaluated at 0, that has to equal our desired initial condition. So here I'm going to plug in for yf, which we've just found was -u of t. And I'm going to plug in, all we know about the homogeneous is that it's a constant times e to the t. But this I'm going to evaluate at 0. This is at 0, and that is at 0. So I'm looking at -1 plus c e to the 0, which is 1, times e to the 0, which is 1, has to equal to 1/3. All right, so this tells me that c has to be 4/3. And with this coefficient, I can determine the natural solution. This is the homogeneous with this coefficient. So 4/3 e to the t, u of t. Okay, so we've got one answer here, and we've got another answer here, and what's left is to combine them. So the total solution, the complete solution, the solution, will be the sum of the forced response with the natural response. So that one way to write that would be 4/3 e to the t minus 1, all of that right-sided. Okay, and one of the nice things about diffie-qs is that they come pre-packaged with a check on your answer. So here we can check ourselves, because what do we know has to be true? Whatever we box for our final answer has to satisfy two conditions. It has to satisfy the inhomogeneous part, and it has to satisfy the initial conditions. So what if we take the derivative of the total response and we subtract the total response from it? Well, we get 4/3 e to the t. The -1 differentiates to 0, and then we subtract 4/3 e to the t minus 1. Well, we get some pretty healthy cancellation. We just get 1. So if you recall that this solution is only valid for positive time, we see that the 1 here is in agreement with our forcing function. Okay, so that gets the check mark. Additionally, we can check the initial condition. What is yt of 0? Well, it's going to be 4/3 e to the 0 minus 1, which is just 1/3. That gets our second check mark. So we found a solution. It meets both of our requirements. It is the solution. So that's all well and good, and it's likely one of the ways you learned how to solve differential equations in your math class. What I'm going to do now is complicate things by talking about a different way to solve differential equations, and that is this zero state and zero input decomposition. So the idea is extremely similar to what we've already seen. Before, we've seen the homogeneous plus particular, and we've seen the forced plus the natural. All of these equal the total solution. What we're going to do now is talk about the zero state and zero inputs, and it will also sum to be the total response. The motivation for doing this is that when you analyze a system in the real world, in the lab, you will often want to decompose the response that system gives you as the response that are due to initial conditions in the system and the response that may be due to any inputs that you're giving the system. And that's not what you get when you try to break it down into forced versus natural. The nomenclature is a little confusing here. It's so confusing that there's a lot of internet resources that will call these two identical, right? They will say the forced solution is the zero state solution, and they'll say the natural solution is the zero input solution. So one of the purposes of this particular video is that these are not equivalent. And that is because the forced and natural solution method only uses the natural to make up the difference from what the forced lacks, right? That was why we called the natural as the extra you need to meet the initial conditions. The zero state and zero input decomposition is a more physically observable decomposition. It's what I would say many engineers would use to solve differential equations. It's because it's what you will actually observe if you give a system the same input and different initial conditions. You can use the zero input and zero state solutions to help you predict what will happen. So enough talk, let's see what happens. So the zero state response, sometimes abbreviated CSR, is a new differential equation that takes the homogeneous part of the old one. So we'll continue the example from last time. dy dt minus y equals x. But the third leg of this trifecta, we've got the homogeneous part, we've got the forcing function. The zero state initial condition is always 0. So I'll put ZS's on these just to make it clear. So this is a new problem with the same inhomogeneous differential equation, but a different set of initial conditions. And by virtue of it being zero state, when you see state, think initial conditions. So if you're looking for the zero state response, you're looking for the response when there are 0 initial conditions, i.e. all the initial conditions are 0. So how does this relate? How does this work in terms of our old problem, where the x function, the forcing function, was the unit step. Well, the zero state solution will have definitely a particular part. So y zero state of t will have the particular that we had before, y p t plus the homogeneous part. This will be the same from the last example. It was minus u of t. And this will have to resolve because we've got new initial conditions. So y zero state at time equals 0 is negative u of 0 plus c hat. I'm going to call it a different c, but the same characteristic mode here. c e to the t evaluated at 0 times u of 0. And this is critical. Instead of setting this equal to 1/3, we're going to set it equal to 0. That's what we mean by zero state. So here we have negative 1 plus c hat equals 0, better known as c hat is 1. So the zero state response, the ZSR of this problem, is e1 e to the t minus 1 times u of t. Right, that's the homogeneous part and the particular part. Now, if we look back up at the other problem, you see that that solution does not appear anywhere. Right? It's not the old forced solution, it's not the old natural, and it's not the old total. So we have a new function on our hands. So I told you that we're going to add the zero state to the zero input, and that should get us the total response. So let's address the zero input now. ZIR. This is again a new differential equation. So dy zero input dt minus y zero input is 0, but the initial condition is the same that we had for the original problem. Okay, so this is what we mean by zero input. You set the input or the forcing function to 0 and only observe the effect of having a non-zero initial condition. Okay, so it won't surprise you that if you have 0 forcing function, your particular, y particular in this case, will be 0. So then the 0 input response can only have a homogeneous part. So it'll be c, a different c, we'll call it c tilde now, e to the t u of t. And the 0 input response at time equals 0 has to meet our initial condition. So this will be c tilde e to the 0, also known as c tilde equals 1/3. So the y zero input is 1/3 e to the t u of t. So box that up, box this up, and hopefully when we sum them as the sum of y zero state and y zero input, I get e to the t plus 1/3 e to the t, so that's 4/3 e to the t minus 1 u of t. And this is the total solution we got using the forced and natural method. Okay. So the question you might be asking is, wait a minute, you're going to trade one differential equation for two new differential equations, each of which solving a new problem. And yeah, that's exactly what I'm asking you to do. The utility, I hope, you will see comes in what happens when I change the initial conditions, or what happens when I change the forcing function. I hope to show you now that if we change the forcing function, you have to resolve the y forced, you have to resolve the y natural, but you don't have to resolve the zero input response. You'll only have to redo half of the zero input zero state method. Okay, so let's try that now. Okay, so in part B of this example, it would be change the forcing function from a positive step to a negative step. Okay, that's the only thing I want to change. I want to keep the same initial condition, but instead of forcing the function with a 1 volt step, I'm going to force it with a negative 1 volt step. This is like you switch the leads on your voltage source, so instead of connecting plus 1 volt, you connected minus 1. Happens to everyone. You'll note that the homogeneous solution has not changed, right? I've changed nothing on the left-hand side, so we'll still have a single characteristic root at 1. What has changed is the particular. So now, the particular will still look like du of t, but when I plug it in here, instead of equaling u of t, it'll be negative u of t. So that makes d, instead of negative 1, it'll be positive 1. And so everywhere I had a negative u of t, I get a positive u of t. Okay, and this is not terribly surprising, right? You change the sign of the forcing function, you will change the sign of the forced response. But because the natural isn't the response to the initial conditions, because the natural is the something extra you need to satisfy those initial conditions, the natural response will change dramatically because of that, not just by a scaling value. So here we've got our new force functions is plus u of t, so this becomes plus 1, and we get now, instead of c being 4/3, we get c being negative 2/3. So I will have to start erasing to make myself remember what's going on. The natural response has changed from 4/3 e to the t to minus 2/3 e to the t. So with that in hand, we can write the new total response. It will no longer be this. It'll be the positive step, 1 minus 2/3 e to the t u of t. Okay, so this is the total response for the forcing function being a negative step and the initial condition being the same. Okay, but what I want to point out is that both the forced response changed as well as the natural response. Now, contrast that with resolving this problem with the zero state, zero input method. Here we're changing the forcing function, so we will have to change the zero state response. That must change. So we'll propagate our fix from last time. This becomes positive u, and we solve that 1 plus c hat has got to be 0, meaning c hat is negative 1. So we get a negative out here. So my new y0 state of t is 1 minus e to the t u of t. And no argument for me. That was, we had to change that to meet the new requirements. However, when we go over here to the zero input response, the fact that I've changed the forcing function from plus 1 to minus 1 changes nothing about the setup of this problem, right? The zero input response, by definition, has zero input. We're just looking at the homogeneous part. So this is also the zero input response in the new condition. And so if we add these up, let me see, where is there room? So let's do y total of t will be the sum of these two. We get 1 minus 2/3 e to the t u of t. And that agrees with our forced versus natural methodology. Okay, so I hope this illustrates some of the utility that if you had the exact same system with these same initial conditions and applied a plus 1 volt step versus a minus 1 volt step, if you were doing the forced and natural solution method, you'd have to resolve both times. Whereas if you do the ZSR and ZIR, you are only required to resolve the part that has changed, and that would be the zero state response, and not the zero input response, because the initial conditions were the same in both times. Okay, thanks everyone.